stuff's due, right? If you can turn in old problem sets, if you want to. Here's the latest worksheet, grade sheet. And some groups have come by and talked to me about the experiment. You can do that if you want. It's optional this time. Right, does anybody have any questions about the finishing up this course? All right. So we're going to do problems. So I've already sent out the quiz for this, right? So that you could be working on it, right? Okay. Because we have static equilibrium involved in it too. Okay. All right. So there's a couple of conceptual questions here. Here's the first one. You've got these particles here. They all have the same mass. This has radius little r. This circle has radius big R. And we want to find the force on the central mass here. So at first this looks confusing, but you stare at it a little bit and you'll realize that there's a pairing of the masses here. For example, look at this mass. What's the effect of this mass and this one here that's diametrically opposed to it? What's the force going to be on that? Zero, right. So they all cancel in pairs. If you go along here, you'll see they all cancel in pairs except that one right there. So they're all paired to give zero force, net force zero, except for that one. So what this means is the force is just going to be big G, the universal constant of gravitation, is proportionality constant in the inverse square law force here. It's the product of the masses, m squared, divided by the square of the distance. And it's attractive, so it's going to point in the plus y direction. So that's why we have the J here. Any questions about that one? The next one, number 2. It's in the problem set assignment, it says number 4. And believe it or not, that may not be a typo. I think I was planning on switching to a different problem, but this is a good problem. And oops, I'm sorry, we're not, forget what I just said. We still have another conceptual question. Sorry. So, this is number 2. This is interesting, okay, and I added something to it, an interesting question to it. We have these two fixed masses here. One mass is twice the other one. And we have a third mass that we're going to bring in. And it happens to have 3 times m, but that's not going to be important here. We bring in, we want to ask this question: where can you put that mass such that, if possible, there's no net gravitational field on it? Okay? Well, you can explore different possibilities here. For example, over here, is there anywhere to the right of this collection here that you can put that mass on the axis there such that the force is 0? No, except at infinity, but that's trivial. We rule that out. Is that clear, right? It's going to be attracted. Both attract it this way. Similarly, you can't put it anywhere here. There's going to be a net force necessarily to the right in that case. What about up here? Anywhere in the upper half plane or lower half plane? No, it's got to be between the two masses, because there the two forces are competing. So for example, if it's in the center, this is going to exert a force that way, and this mass is going to exert a force that way, so they'll be competing. Now, in the center, it's not going to give 0 force, is it? Which way is the force going to point? Right. To the right, because this one's greater. But if I move it over here, eventually there has to be a balancing point where there's no net force. How do I know? How do I know that? How do I know that it has to exist? Well, you can do the math, okay? And you can easily do the math here. It's not hard. But this is a conceptual question. We're not going to do it. here's the reasoning. You go to extremes. We've seen this a number of times in this course. And it's this common thing that physicists do. Suppose I put it closer and closer, very close to this mass. Where's the force got to point? This way, right? Because it's an inverse square law force. It's getting greater and greater. And it actually goes to, for point particles, it'll go to infinity here, right? So I know, if I know here the center, the force points to the right, and I know sufficiently close to this mass, it's got to point to the left. There's got to be somewhere in between that the net force vanishes. It has to be. Because it's just continuously changing here from pointing to the right to pointing to the left. So somewhere here it's going to vanish. And you can solve for that, but we're not going to do it, like I said. Now this is not the story, the whole story. This is the whole story in the textbook. But there's another question you can ask here. Okay, and you should always think of this whenever you're dealing with a system that's in equilibrium, like this mass that we've brought. Oh, I'm sorry, there's one more question here. I think there's another question. Hold on, let me look at this. So the answer to the question here, does it depend upon the mass of the particle we're moving around? Does the location where the force vanishes depend upon the mass? No, obviously not, right? Zero force is zero force. So you would get the same answer no matter what mass you have here. Okay, so that's this, okay? And and there's another off-axis. It's clear. You put a mass here, you got an attractive force here, attractive force. So there's no way those vectors can cancel. They're not collinear. The only way they're going to cancel is if they have to be collinear, anti-collinear. Lying on the same line but pointing in opposite directions. Okay, now for something that's interesting here. So anytime you encounter a system in equilibrium, it's useful to usually ask, is the equilibrium stable? Just because the force vanishes doesn't mean that if there are slight perturbations, it will stick around at that point. So the standard analogy, as I think I've said before, is in a gravitational field, you can have a ball in a valley here. This is stable. If you perturb this a little bit, or just due to natural fluctuations, it's not going to run away. However, if it's on the top of a hill like this, these are both equilibrium situations, but they're very different, right? This is unstable. Slight perturbation and it's gone. What about this? So we know there's a point here, somewhere to the left of the center, where it's in equilibrium. Suppose there's no force. Suppose, let's say we imagine it displaced a little bit to the right. What's going to happen? There'll be a force. There will be a force. Which way does it point? That's the critical thing.
To the right?
Yes. Did everybody see that? Here the two forces are balancing. By moving it over here, that force gets stronger. This force gets a little stronger. This one gets a little weaker. It's an anti-restoring force. It's unstable. And in fact, this is supposed to be a famous theorem, but my modern physics students don't know about it. They should. It usually comes up in electricity and magnetism. It's actually at the intermediate level. I don't think you'll see it next quarter. Do you take 1322 next quarter, the electricity and magnetism course? Yeah, I don't think you'll see it. But you can prove for masses here in the gravitational case, or in the case of electrical charge, that is impossible to, with any arrangement of masses, it doesn't matter what arrangement of masses you have here. If you've got a point of equilibrium where there's no net gravitational force and you put a little test or probe mass there, it will be unstable. There'll be at least one of the three directions, it will be unstable in that direction. It is impossible to have it stable. And this is important because often we want to levitate something. We want to, for example, levitation in a gravitational field. You can use charge, or you can use a magnetic force too. The Earnshaw's theorem is true for a magnetic force too. it's impossible to stably levitate something in all three directions. So you have to be more clever. If you want to levitate something stably, you've got to be more clever. And there are ways, but there's no static. You have to, it has to be a dynamic thing. This is a static arrangement here. Impossible. And it's interesting that that can be shown in general. It doesn't matter. Any distribution of mass. You may wonder, how can you prove that? Well, it's, you know, got to take some more physics. Got to go to the intermediate level in physics to find out. And it turns out the proof is actually very simple. The general proof. Okay, any questions about that? So this one is the one where I think I was planning on changing it, but I looked at this and I think this is a good problem. We're going to stick with problem number 2. So here's the problem. Here's the sun, the earth, and the moon. This is not to scale, right? I should have put some squiggly lines here. So this distance is much greater than that distance. Big R is much greater. Should have written that in here. Big R is much greater than little r. And the problem here is to find the ratio of the magnitudes of the force of the sun on the moon divided by the force of the earth on the moon. That's the problem. So here's the information we need. You'll notice the mass of the moon is not on here. And can anybody see why we don't need it? We're just going to deal, well, you'll see, we're dealing with the ratio. It will cancel out. You'll see that. So the force of the Earth on the moon is big G. It's the product of the masses, the mass of the moon, the mass of the Earth, divided by the square of this distance. It's approximately a circular orbit. It's the magnitude of the force. The magnitude of the force of the sun on the moon is very similar, except we have, instead of the mass of the Earth, it's the mass of the sun. So it's not obvious which one's going to be greater here. The mass of the sun is much greater, but it's much farther away. So it's not obvious. So to probe that, we naturally take the ratio. That's the simplest thing to do. And you can see that the mass of the moon will cancel out. So will big G. And we just get an expression that involves the ratio of the masses and the ratio of the radii, or radiuses. So here it is. We plug the numbers in. And again, we have we don't know what's going to happen because this is big, this ratio is big, but this ratio is small. Right? So you just punch it in and you get, it's interesting, it's on the order of unity. It's, you know, this could have been a large number, very large number, or a very small number, but instead it's roughly on the order of unity. Is that a coincidence? Probably, but I don't know. Coincidences make physicists feel uneasy, like they're missing something deep. And I don't know. I didn't think about that until right now. I'm going to make a note of this. I think it's almost certainly just a coincidence, but there could be a connection in the formation of our solar system when it was formed, you know, billions of years ago, right? Okay, so we get a number, it's 2.2. And it seems like we're done, but for some reason, last year when I was teaching this course, I looked on the internet. I don't know why, and I don't know what I was looking for, but it was in connection with this problem. And I found this question all over the internet was, okay, so why doesn't the sun pull the moon away from the Earth? I never thought of that. I don't think it's in the problem here, right? Does anybody see this? What is this, 13.2? No. But it's kind of an interesting question. Yeah. So what's the answer here? This force is greater than this force, so why doesn't the sun pull the moon away from the Earth? Well, Yeah, well, here's the answer is that, first of all, you have to realize that it is pulling on the moon, okay? Because they're both moving around the sun. Otherwise, they'd just move off in a straight line, right? So the sun is pulling on the moon. It doesn't pull the moon away from the Earth because it's also pulling on the Earth with causing the same acceleration. The gravitational field here is because the sun is so far away, the gravitational field of the sun is approximately uniform here. So it pulls both the Earth and the moon with the same acceleration, and that's the centripetal acceleration of the Earth and the moon going around the sun. Hey, you never know what you're going to find when you go on the internet, right? You never know. Okay, any questions about that one? All right, so here's a classic problem. This is a sphere, and it's got a hollow section here. So this is a sphere of some material. It doesn't really matter. It's some uniform material. I guess this is all. Oh. We're given the, hold on a second here. So we're given this big radius r. This hollow section the surface passes through the center, so its radius is half of the main section there, right? With a solid material. And yeah, we're given the mass of the sphere before hollowing, all right? So that means we can find the density. If we know this is the mass, this m0 here denotes the mass before hollowing. All right, and we want to find the force. There's a little mass here, a mass on the axis of this distribution of mass. This is an axis of symmetry of this distribution of mass. Because of the symmetry, the force must be directly must lie along this axis to the left. It's got to be by symmetry. Because this, you can rotate this object. This is an axis of symmetry of this object here. So how do we find this force? How do we find this force? Well, you could integrate. Good luck. Look, every little element here contributes to the force, every little mass element. The problem with that integration is, the boundaries here. The boundary that you have to integrate over it has this is the inner surface, this is the outer surface. It would not be an easy integral. I don't think it would be an easy integral. But there's actually a much easier way of doing it, and it's using the principle of superposition. So I know that which is simply that the total force here is the sum of all the individual forces for all the mass elements here. So you want to be clever here, and the way you want to view this hollow sphere is as a superposition of a uniform sphere of radius big R. We find the force due to that, and then we subtract the force due to this sphere right here with the same material. When I superpose these two things together, because when I add them to create this, because of the minus sign here, it's going to cancel all the mass in there and give us 0. So the net force has to be the attractive force due to the solid sphere. And then it's going to be less because of the hollow, and it's going to be less precisely by the magnitude of that force. So this is what we can write down. I'm going to call this the force due to m0. And we're given m0. That's the unhollowed sphere. The net force is going to be the force due to this. And it's going to be less because of its hollow sphere, and it's going to be less precisely by the magnitude of this force. So you've got to be a little careful here. This is clear, or this distance d. The center, we're using a spherical shell theorem here. The center of this mass right here is not at d. It's d minus big R over 2. Right? It's this distance right here. We imagine all the mass to be concentrated at the center of mass, which works for a sphere. So that's the basic idea. The force is going to be what it is if the sphere was not hollowed out. And the correction here is due to this hollow part, is going to reduce it, and it's going to be precisely by that amount. Now we need to know M1. How do we get M1? Well, some of you might be able to see this. Because it's 1/2 the radius of this, it will be 1/8 the mass of M1 will have to be 1/8 M0. Because the mass is proportional to the volume, which is proportional to the cube of the radius. But if you don't see that, here's the standard way to do it. M1 is going to be the volume of M1 times the density of the material, which is, this is some uniform, we're assuming a uniform material here, right? Whatever it is. Do I know the density? Yeah, I know it because it's going to be this mass divided by that volume. That's the density. So if you take this expression, plug it into here, you get a lot of simplification, and you get, I'll let you do this if you're interested, you get precisely the 1/8, which it has to be, because it's got 1/2 the radius, and the volume's proportional to the cube of the radius. So it's going to have, it has to be, and the volume's proportional to the mass, so it has to be 1/8. But this is a sort of standard way of doing this, if you don't see that. So now it's, here's our final algebraic expression. At this point, I think we can plug in, we can algebraically simplify. I'm gonna do that, I think, on the next page here. Yeah, we can factor out this expression. Yeah, and we're going to it's natural to do that, factor out this distance, which we're given here. Now you'll see that I've done something here. To factor out d squared, I've had to do a little bit of algebra here, right? To bring this d outside here, I've got to divide by d in there, right? So this is simple algebra. You can verify that. And that's why I get this. And this is a nice clean form. This is all purely dimensionless number. This is a dimensionless number here. So this is a cleaner way of doing it. So at this point, we just, I think, plug in the numbers. And there's, I don't know how this happened. Please note there's a mistake here. This is not 4 minus 10 to the minus 2. It's 4 times. Yeah, that should be times. Please correct that. Everybody see that there? This right here should be times. And then you punch this in. I had to punch it in about 10 times last night. I don't know what it was. I kept getting different answers. Has this ever happened to you? And you know, it's like a Twilight Zone kind of. Oh, do you guys know what the Twilight Zone is?
Oh, yeah.
Okay. All right. Yeah, right. Yeah, I don't know. You get it, and I just kept punching in, and I checked the solutions manual. You know what I mean? Well, finally, this is the right answer. Okay, and I was just making a mistake, a different mistake every time. You know, it was just, I was trapped in this Twilight Zone. So, okay, any questions about that one? So that's kind of a classic problem. It really you utilize the principle of superposition. Any questions or comments? Okay, oh, I promised you a problem like this. This was if a planet or some astronomical body is spinning fast enough, and you're on the equator, let's say, and you release something, some object from rest, if it's spinning just the right speed, that mass can just stay there. It would be in uniform circular motion. So here's this is the axis of rotation. So if I, and we'll go through I think the math, we need to look at the math here for you to believe this. But the faster, first let's do it this way. Start off with no spin, okay? I release an object from rest on this spherical body here, spherically symmetric body. It's going to have an acceleration, little g, right? And we can calculate that. We have a formula to calculate that in terms of big G and the mass and the radius. Remember, that's a very useful formula. Now let's suppose it's spinning. The thing you want to recognize here is that little g is defined, actually it is what you would measure as the free fall acceleration. So a practical, realistic quantity. And you think it's going to have the same acceleration if the planet's rotating? It's going to be less, right? You probably have an intuition, maybe you have a feel, maybe not. No one's really saying anything. But maybe we should go to extremes here. You spin it more and more, okay? Eventually, there's going to be some precise speed that if I release it, I should have brought the globe in. If I release it from rest, it's just going to move in uniform circular motion with the surface of the planet. G will be 0, little g will be 0. So we can easily calculate that, okay? First, I want to point something out here. In this problem, this is a neutron star, which is kind of like a giant nucleus. It's extremely dense. And we'll see an aspect of that in the end here. If it's spinning, and I think believe this is where pulsars come from. This thing sends out a beam of electromagnetic radiation. And the frequency at which the beam hits the Earth, if it does happen to hit the Earth, is like on the order of once a second. So it's spinning. It's spinning fast. You know, our Earth is about a month for the Earth, the Sun to rotate. I think it takes about a month. Does anybody know that?
28 days.
What?
28 days.
That's about a month. Okay, thanks. Wait, 28 days. Isn't that the same what it takes for the moon to go around the Earth? Is that just a coincidence? Is that right? Huh. Yeah, here's another one for you. The moon spins, right? It spins at the same rate that it goes around the Earth. We always see the same face of the moon. Oh, that's just a coincidence, right? What do you think? No. That's an example of what's called, they now call it synchronization. Used to be called mode locking or phase locking. Now the popular word is synchronization. That's a phenomenon that occurs in a lot of different physical systems for different reasons. But it had to do with in the formation of the solar system. So as you imagine spinning this further, greater and greater, eventually there's going to be and this will be intuitive for you, eventually some mass is going to depart. Where is it, as I slowly imagine increasing the speed, where's it going to happen? Where's the departure just going to happen? Well, the greatest acceleration is right on the equator here. Mass here is not going to be affected. Okay, so it's going to be a gradual effect as you move down along here. The mass is just going to start to leave. The mass is on the equator. So that simplifies the problem here. We can look on the equator. All right, and here's the situation. Force diagram, right? Here's the picture. Here's the force diagram. I look at some little mass here. Can be little, doesn't really matter. And I see that there's, in general, two forces on it. There's an attractive gravitational force due to the body here. And then there's a normal force due to neighboring elements right here of the body, right? That prevent it from just going into the center here. So here's my force diagram. And Newton's second law tells me that the net force has to be the mass times the acceleration. And the acceleration is the centripetal acceleration. It's v squared over r. But here it's much more convenient to use omega squared r. Remember? Because v is equal to omega r. V squared over r is equal to omega squared r. So now the next step here, this is general when there's a normal force. We're interested in the special case where the normal force just goes to 0. As you increase the angular velocity, it's going to get less and less. You can see that here. As I increase this is going to have to get less and less. Eventually this will go to 0, and that's what we're interested in. And that's when this mass is weightless. And incidentally, you are weightless too if you're standing on this thing. But I'll tell you right now, you won't be alive if you're standing on a neutron star. And we'll see that in a moment. Okay, so here it's just calculate. Here we just calculate. In this particular problem, we're given the angular velocity, we're given the radius, we want to find the mass of the neutron star. So this is one equation and one unknown, and we can find the mass, okay? Now I want to point something out to you here. They don't ask, I don't think they ask you to do this. Yeah, they don't ask you to do it. I might ask you in the problem set. I don't think I did. But let's suppose the neutron star were not spinning, okay? Then we can use our formula. This is the formula I was talking about earlier. It's a great formula here, right? We can find the acceleration due to gravity. In fact, this is how Cavendish weighed the Earth, right? Because we know that this is 9.8 meters per second. That's how he was able, by determining big G. Before Cavendish, there was no reliable determination of G, so this was like one equation and two unknowns. But once he measured G, the first thing he did was he found the mass of the Earth, right? So let's just calculate this for the parameters that we have. We know the mass, we know the radius, so this would be the acceleration on the surface of the neutron star in the absence of spin. And I want you to look at this number here. How do you think how do you feel about this number? Or how would you feel? I think you'd be just you'd feel down. That's huge. I don't think our bodies could handle that. You'd be smeared out on the surface. Okay, any questions about that one? Okay, the next one is 38. Okay, a lot of interesting planetary stuff here. So this is a hypothetical planet. It's called Zero. It's got a mass. We know the mass. We know the radius. It's got no atmosphere. And we're going to launch a 10-kilogram probe vertically from the surface. Now, when we talked about escape speed, this doesn't have to be vertical. But in this problem, the way what we're after here you need to recognize that it's vertically launched. So what's going to happen? It's going to take off here, and it's going to slow up because there's a gravitational pull on it. So it's going to decelerate. So it can come to some point here and stop and come back, or it can just go away and never return. And how would you know? How would you know which of those? There's two different possible states here, One, it comes back and crashes into the planet, and one, it goes away and never comes away. So what separates those two? What's the separatrix? Which I wrote into the lecture notes just once in the lecture notes. I haven't sent them out yet because, I will, the revised lecture notes. How do we know? How would you calculate that? Anybody? I just talked about it. You'd compute the escape speed. There's an escape speed here that you can compute. We have a simple formula for it that we got by energy conservation. You would determine that value and you would compare it to V naught. Do we know V naught? Yes, we're given the initial kinetic energy. The authors should have added the word kinetic energy. We're given the initial kinetic energy. So we know the initial velocity. You would compare the velocity to the escape velocity. If it's greater, it's not going to come back, okay? And if it's less, it's going to eventually come to rest and then come back and crash into the planet. Okay, well that's not the problem here. The problem, I just want to point it out. The problem is, first part is, what will its kinetic energy be when it is some distance from the center? Okay, so that we're given some distance here, and we want to know what the kinetic energy is. It's going to be less, but how much less? What is it going to be? Okay, well this is classic energy conservation, right? We know that the total mechanical energy, the kinetic plus the potential energy, is going to be a constant here. So what that means, I skipped a step here, so let me write it down. It's a simple step, but maybe I better write it down. So conservation of energy here tells us that the initial energy is going to be the final energy. So this allows me to determine the final kinetic energy. I just bring this over here, and I get this. And we know or we can calculate it, we're given this, and we can calculate the change in potential energy. The potential energy is for, in this case, for a gravitating body in general is given by this. We derive this. And the convention here is that the potential energy is 0 at infinity. That's a choice that we make, a very convenient choice that we make. So we can calculate here, we can write down, we're given this, we're given the initial kinetic energy. We know the initial radius, this R0 is just going to be what we call capital R up there. And we're given this final distance, we're given that. So we can calculate everything. We can find the final kinetic energy. And here it is. And the first thing we should do with this answer, and I'm surprised that I didn't write this down, is we should compare this to something. What should we compare it to? Anybody? Yeah, it better be less. If it were greater, we would have made a mistake. So that's a check. The fact that this is less than K0 gets a check mark. Okay, I know it may sound silly to you, but you can make mistakes, right? For example, you might have made a mistake with this sign here. It's going to involve the difference here. You might have made this minus and this plus. That would do it, okay? Then it would appear here that that's going to give you a greater value, and it can't be. So that's why people do these checks. It's easy to make mistakes. Part B is so now we're going to specify the maximum distance. So we want to know how much energy we have to give this. So it'll momentarily come to rest at some distance here, and then it'll come back. So again, we use, here's energy conservation. All right, and in this case, the final kinetic energy is 0. That's going to be the turning point there. We're choosing that to be the final point. We're given the distance. And now we can solve for the initial kinetic energy. And it's equal to this. Okay, any questions or comments about that one? Okay, the next one, another planetary type problem. This is 43. So Phobos, this is an actual moon. I guess it's so small they call it a satellite. I don't know, they have trouble, with what they call a planet. Remember Pluto? So my generation, we got really upset because we were taught that Pluto is a planet. And then like 10 years ago, or I don't know when it was, all of a sudden people are saying it's not a planet. Well, that really upset a lot of people, okay? I don't know, it's just words. But I don't know, they call it a satellite here. Maybe it's actually satellite made by ancient aliens. Probably is. Yep. We have a circular orbit where we know the radius. Okay, and we met in a period. Now I want you to notice something here. This is stuff that can be measured with a telescope. Okay, you can measure this radius, and you can get they're quite accurate. I think they can determine radius pretty accurately, but they can get a really accurate time, I think, on the period here. And it's given to us in hours and minutes. That's, of course, Earth time. So first thing we want to do here is convert this to seconds. All right, so you can do it any way you want to, just make sure you get the right answer. I get seconds here. And now, what's interesting about this is we can use Kepler's third law to determine the mass of Mars. And this is one way of finding the masses of astronomical bodies. Now, I don't know much about this, and I didn't look it up on the internet. There probably are other ways, but this is I think the standard way. I would guess. You know, how do we find? You know, we know the Earth is special because we're on it, so we know how to find the mass of the Earth, right? Cavendish showed us how to by determining big G. You know, we were able to do that. But what about other planets? How do we find their masses? Well, I think the common way to do it is what you're seeing right here. So this is very practical. So here's here's Kepler's third law, and again, there's an assumption here that this mass is much greater than the mass of the orbiting mass. There's a generalization. It's not difficult to generalize that, but and we'll see in the next problem, we'll see some evidence of that. But we're just going to stick in this class with the simple Kepler's third law, where this mass is much greater than that mass. And here it is, the square of the period is proportional to the cube of the radius, and we're doing uniform circular motion here. So we know everything here except the mass. So we solve for the mass, plug the numbers in, and we get this mass for Mars. And I assume this is accurate. I didn't check this. But I'm sure if you check this and look in the book, you'll find this is close to the accepted value. We did it to 2 figures here. I think it would be exact to within 2 figures. It's about 1/10 the mass of the Earth. Okay, any questions about that? Finally, I think this is the last problem. Right. So, I haven't checked in maybe 20 years. The last time I heard something about this was, it turns out that in our universe, roughly half of the stars out there are binary stars. Do you guys know this? Maybe they've refined that since I heard about it. I didn't check. Maybe Luke is checking right now. But anyway, I don't think it's changed. I just remember this from a couple decades ago. Roughly half of the stars out there are binary stars. And it's probably understood, you know, due to their formation, they're coalescing from this hot gas, and the gravitational is starting to coalesce. They always have some angular momentum that's going to be conserved, right? So the mass is getting closer, and the momentum is conserved. Remember the weights on the platform that you can sit on, which is really nice. So almost always they're going to have some spin here, and it's probably somewhere in the dynamics here that it's popular due to the spin here, for this to coalesce into 2, going around like that, right? And they're probably going to tend to be equally massive now that I think about it, but I don't know about that, but it seems reasonable. So that's this is not some unusual event here. It's actually popular for stars to be binary stars. So we're going to take a simple case here where they are equally massive. The total mass of the star is 2m here. And we're going to take each of these masses to be the mass of the Sun, which is about 2 × 10⁻³ kilograms. We're going to take the case of uniform circular motion. It doesn't have to be that way. They can be doing this. Whoa. And what's the center of mass doing here? Not moving, somewhere here. See, whoops, I just hit the center. Yeah. Okay. Yeah, they can be doing that. Okay. You want to guess what this path is here? Now, we don't know this, but you can probably guess. Yeah, it's an ellipse. Pretty sure it's an ellipse. Okay. But we're going to take the simple case here of uniform circular motion. So they just go around like this. And we're given that the distance here, excuse me, this diameter here, this distance is the same as the Earth-Sun distance. So that means that the radius is going to be half of the Earth-Sun distance. Now you might think, well, why don't you just deal with the diameter? Well, you can see there's a number of calculations here, and I think it's better to just go to the radius, okay? I think you'll be less likely to make a mistake. So that's why I'm going to deal with the radius here. Okay, so that was quite an introduction there. What's the problem? This is number 55. What's the period in Earth years? What's the period? Okay, well, we can't use our simple form of Kepler's third law here because the masses, one mass is not much greater than the other mass. Right? In fact, this is about as far as you can get from the standard Kepler's law. As I mentioned before, there is a Kepler's law that can handle this, but we're going to derive it in this case, essentially, as you'll see. So we got to go back to basics here. You know, you're probably looking for a single formula that will tell us the answer here. It doesn't exist for this course, okay, for our simple course here. We're going to have to go back to basics. What's the force? You know, this is and Newton's second law. So the force of, there's an equal and opposite force here, of course, and it's given by this, universal constant of gravitation times the product of the masses, which is m squared, divided by the square of the distance. So it's 2r squared. And Newton's second law tells us, if you focus your attention on either one of these masses here, I got to have F equals ma. So this force has to equal the mass times the acceleration, which used to be v squared over r for us, and it still is, but it's better here to deal with omega, the angular velocity, because that's simply connected with the period, and that's what we're after here. So we're going to use, as I mentioned before in a previous problem, we're going to use, instead of v squared over r, omega squared r. Now, this is Newton's second law, but we know the force. Here it is. So we simply plug this expression into here, and we've got, here's what we get, and we've got one unknown, it's omega. Actually, we can simplify this. Here it is, here's a simplified version. That's the first thing you should do when you see something like this. First look for some simplification. Here it is. Now we're going to substitute the fact that omega is 2 pi over the period, which we've talked about a number of times before. When we do that and solve for t, we get this expression here. What does this look like to you? T squared is proportional to r cubed. What does that look like to you? Kepler's third law, right? But I want to point something out to you here. The constant of proportionality here. It's not our Kepler's third law constant of proportionality, because that only holds when the gravitating mass is much heavier. And in fact, it's 4 times what you would get in our Kepler's third law. It's 4 times. All right, so we didn't know that. You know, ours Kepler's third law is only valid when one of the masses is much greater. So we derived it here, but it's not surprising that we get a Kepler's third law, but it's different. The standard Kepler's third law does not apply here. So at this point, we just plug the numbers in, and this is all SI units, so I'm going to end up with seconds, and I convert the seconds, and here's another, I don't know, another coincidence. I don't know if you guys have ever noticed this before, but the number of seconds in a year is close to pi times 10 to the 7th. I think it's just a coincidence? I think so. Okay, I think that is a coincidence. I can't imagine. You can imagine. Yeah, you can imagine there's a connection. You know, a year is what it takes for the Earth to go around, and you can see pi in there. Right? But I'm pretty sure it's a coincidence, okay? Some coincidences are just coincidences. You know, it's like the Freud thing, right? What he said. You guys know that. Sometimes a cigar is just a cigar. Yeah, it's classic, okay. So I don't know if that has any relevance here, but it's just occurred to me. So anyway, it's roughly a year. Yeah, it's on the order of a year, which is kind of interesting. Okay, any questions or comments about this one? Okay, does anybody have any questions about the course or about the due dates and everything? Remember, check that sheet. Check it carefully, because